Okay, welcome back, everybody. So we're going to start up 2.3 and finish it. And I mean, we were supposed to continue on 2.2 today, but I guess we uh, uh, are ahead of schedule. So maybe we can spend some time at the end doing some extra practice of these things. Okay, do we all remember long division? Didn't we have a great time with it? Did we ever have to do polynomial long division? Did anybody do that? Well, we're gonna do it. It's a fun one. And you might be thinking like, oh God, so we're just gonna have to deal with this once and I'll remember it. I'll memorize it for now and then I'll forget about it in the future. That's not gonna happen. Long division shows up every once in a while in every area of mathematics. If you plan on taking 181, you'll probably have to use it. We're going to use it a little bit. And when we talk about slant and oblique asymptotes, we'll work with it. In 182, you will definitely use it. And then in future math courses, you will also use it. So it is something that is going to keep showing up. So it is important to talk about it. And it's very, very important in terms of polynomial, like our understanding of polynomials. Polynomial long division, in particular, the division algorithm, helps us get a lot of important theorems. So the division algorithm for polynomials in particular is let P and D be polynomials such that the degree of D is smaller, is less than the degree of P. Then there exists unique polynomials, Q and R, such that the way that we're going to use it is that P of X divided by D of X is equal to Q of X plus R of X divided by D of X. That's the way we're going to work with this formula. That's the more applicable one. In mathematics, there are sometimes formulas that have a practical version of them and a proving version of them. The other alternative, or P of X is equal to Q of X times D of X plus R of X. So in mathematics, I think I might have mentioned this before, but when you get into upper division mathematics, it's less about doing number stuff, like doing calculations, and more about proving certain properties are true. So my upper division courses, it was all like there were very little numbers. It was all prove that this is true for any arbitrary thing. So if you're trying to prove something, the formal definition of the division algorithm, P of X equals Q of X times D of X plus R of X, the one that I've written in brackets, that's the more useful version for proving stuff. But for applicational purposes, which is what we're interested in most math courses, up until you get into 400 level more math courses, is the one that I've highlighted or boxed in blue. That's the way we're going to be using it. So the names of these things are as follows. P of X is called the dividend. Dividend. No, dividend. Couldn't spell it for a second there. Dividend. For whatever reason, I can't think of a good reason why it's called the dividend, but mathematics is weird sometimes. D of X, the thing that you're dividing with, that's called your divisor. That name makes sense. Q of X is your quotient, and R of X is your remainder. In particular, your dividend polynomial, your divisor polynomial, your quotient polynomial, and your remainder polynomial. Now, if you remember the old algorithm, right, for long division back in the day, every number is technically a polynomial. It's just not a very exciting polynomial. It's a degree zero polynomial. And because that's true, the old algorithm can kind of give us some insight on how to do the new algorithm. And by the way, if you already know how to do polynomial long division, kudos to you. This will be mostly a review, but otherwise, we're going to go through it. So if you want to go back over it, and just as a fun little tidbit, one thing I remember, I used to teach. I used to teach for CSN on the satellite campuses, specifically the Palo Verde one over in Summerlin. I taught there, and I would teach the night courses for a little while before I had my son. And I finished teaching, and I was walking out with a bunch of textbooks because I didn't have an office at that point. And there was a young boy with his grandmother, and they were out for a walk. And they saw me holding my textbooks and stuff, and they said, "Are you a teacher?" I said, "Well, yes, I am." And they asked me what I was teaching. I said, "I'm a math teacher." And he said, "Do you know how the division algorithm works? Do you want to know how it works?" I said, "Well, of course I do. Of course I want to know how the division algorithm works." Because he just learned it. So he told me the whole process, and it was great. And me being a teacher, I asked him, "Well, why is that? Do you know why that's true?" And his answer was perfect. It was because my teacher told me to. Because my teacher told me so. That's a great answer, my dude. That you're going to go far with that answer. It's not that it has anything to do with real math, but like and the math behind it. It's because your teacher told you so. Excellent, excellent answer. Anyways, how it works as a reminder, in case it's been a while, is if you have 805 divided by 3, and I've chosen these numbers very specifically, by the way. You first figure out how many times does 3 go into 8. And it goes into it 2 times. And so you write a 2 up above in the 100 spot. And then you do 2 times 3 and you get a 6. And then technically you're supposed to write 600 because 2 sets of 300 go into 2 sets of 3, which would be 600 goes into 800. And then you subtract it, you get a 2 left over, and you bring all the other numbers down. Then you ask yourself, how many times does 3 go into 2? It doesn't go into 2, so you have to look towards the next digit. It goes into 20 6 times because 6 times 3 is 18. You put that down below, take the subtraction, and then work down again. And you repeat this process until you get down to a 1. And then you ask yourself, how many times does 3 go into 1? It doesn't. And there's no other digits to look at, so we're done. That's the remainder. So the 268, that's your quotient, and 1 is your remainder. And so it fits into the division algorithm. Here, P of x is 108, D of x, your divisor is 3, 268 is your quotient function, and R is 1. So this process of figuring out how many times does your divisor go into your dividend is very, very similar. So here's how we do it with a polynomial instead. So this time what I've got is 14x squared minus 9x plus 2 divided by 7x minus 1. Step 0 is if there are any missing powers of your variable in the dividend. Specifically in the dividend, it doesn't matter too much with the divisor. So like the dividend being 14x squared minus 9x plus 2 and the divisor being 7x minus 1. If there are any missing powers, then you need to make sure you put a placeholder for them. And we'll see that in an example in a little bit. But this one, all the powers of x are present in the dividend. There's an x squared, there's an x to the first power, and there's a constant term. If this was missing, we'd write a plus 0x. But it's not missing, it's there. And I'll explain why once we see it in action. So not needed here. Smiley face. So I'm going to color code these things. Step 1, I'm going to do in blue. So let's set up the division, the long division. So 7x minus 1 is our divisor. That goes on the outside. And then we divide it into 14x squared minus 9x plus 2. Step 1 is going to be divide the leading term of your dividend, so 14x squared, by the leading term of your divisor, 7x. So 14x squared divided by 7x is equal to 2x. 14 divided by 7 is 2. X squared divided by x gives you 1x left over. That's why it's 2x. And I will place that above the 9x. Treat every power of x like a digit. It's like a digit of a number. So what am I doing here? In the same way above where I was trying to take how many times does 3 go into 8, I'm saying how many times does 7x go into 14x squared? How many times does 7x go into 14x squared? 7 goes into 14 2 times. X goes into x squared x times. And that's where we get that. So what's actually happening is I'm dividing them to figure it out. But as you get better and better at this, you don't need to do what I've done in blue under step 1. Then what you're going to do is the same thing you would do in the normal division algorithm. Once you've found out how many times 3 goes into 8, you'll multiply them together and get 6. So in the same fashion, now that we found out how many times 7x goes into 14x, we're going to multiply our divisor, 7x minus 1, by the result in step 1. So we'll do this step in, let's do green. So I'm doing it off on the side here. So 2x times 7x minus 1, that is 14x squared minus 2x. And I will put that right below, 14x squared minus 2x. So just like before, I'm trying to figure out how many times does 7x go into 14x squared? It goes into 2x times. Then I'm doing the multiplication. 2x times 7x minus 1, that's 14x squared minus 2x. Then we're going to distribute the minus sign. So in red, I'm going to do this step. You're going to subtract the result from step 2 in the division. So we're going to subtract it from 14x squared minus 9x plus 2. So I'm going to subtract this. And then make sure you distribute the minus sign. This is one place where they really differ. In the previous example with normal long division, with normal number long division, there isn't multiple terms. There's just one value, 6, then 18, then 24. It doesn't have any extra stuff. But now we're subtracting a collection of terms. So that minus sign has to get distributed into both. So the way I like to read it is I look at it and say 14x squared minus 14x squared. Well, those are going to cancel. And that's kind of by design. If we found out how many times 7x goes into 14x squared when we perform the division algorithm, that should cancel out. If it doesn't, we did something wrong. Then I have to do this one. Negative 9x minus negative 2x. That's really negative 9x plus 2x because it's subtracting a negative. So I get negative 7x. Does everyone see that? Does anybody have questions on that so far? Yes.
Well, minus that subtraction sign distributed into the 2 when it just been
You got it?
Yeah.
You explained it to yourself? Good.
Yeah.
Good. That's step 3. Now, step 4 is the last step, and it's going to be an iterative process. This happens over and over again until you can't do it. So pull down any remaining terms and repeat the process until you can't do it anymore. So I'm going to do this step in purple. So I bring down the 2, and then I repeat. How many times does 7x go into negative 7x? Well, it goes into it negative 1 times. So I'll add that little remark here. Negative 7x divided by 7x, that's equal to -1. Then what I'll do is, now that I've found the number of times that 7x goes into -7x, I'll do the multiplication. So -1 times 7x minus 1, that's going to be -7x plus 1. And then I'm going to subtract that. And the 7x's will cancel. The -7x's will cancel because it's -7x minus -7x, which is usually plus 7x. So they cancel out. And then, do I get 1 or do I get 3? 1. That's right. Because it is 2 minus 1. I've had students write this in the past. And so what they do instead is they write plus 7x and minus 1. They distribute the minus sign and write it above it. But that doesn't work for me personally, because then I forget whether or not I had a minus sign to begin with. Like, do I minus this one or do I minus this one? That's my problem with it. But if that's the way it works for your brain, awesome, do it. And so we should get a remainder. We get a 1. And we ask ourselves, how many times does 7x go into 1? And it doesn't. 7 doesn't go into 1 and x doesn't go into 1. So we're done. This is our quotient. So we have our quotient. And this is our remainder. So the division algorithm says that the dividend, 14x squared minus 9x plus 2 divided by 7x minus 1 is equal to our quotient, 2x minus 1, plus our remainder divided by our divisor. Any questions on that? Okay, let's go ahead and do some more practice of it. Okay, and this one, 27x cubed plus 9x squared minus 24x minus 10 divided by 3x squared minus 2. So I'm actually going to save this one. I'm going to work backwards. I'm going to let you guys work through this one yourselves after we go through another one. We're going to go through B together. One thing of note is, notice that the divisor in part A, the 3x squared minus 2, it's missing an x to the first power term. It's not necessary for you to put a placeholder there. It doesn't hurt to do so, but it won't actually end up affecting the problem in the long run. But it's still useful to do. So this one, we'll do B together. B. 3x cubed plus x plus 5 divided by x plus 1. Problem is that the dividend, note, there's no x squared term. We need a placeholder. So what I mean by that is we're going to set the long division. So x plus 1 divided into 3x cubed. Then I'm going to put a plus 0x squared plus x plus 5. Why? Why did I do that? Why did I do that at all? So it is okay, technically speaking, to forget to write the placeholder. It can work. You can get through the problem doing that. That being said, I've never seen a student successfully do it when they forget to put the placeholder. Because when you forget to do it, it gets all muddied up. Because you'll have x squared terms where you shouldn't. And it'll look all choppy and it'll get confusing and it won't be necessary. Better yet, to understand why we do this, imagine each power of x is like a digit of this quote unquote number that's a polynomial. Thinking back to this example, I deliberately chose 805. So there's 8 100s, 0 10s, and 5 1s. Even though we don't have any 10s, do we still write the 0? Yes, because it's a placeholder. It has a place in the number. So even though there are 0 10s, I still write it down. It's just we are lazy mathematicians. We don't like to write things if we don't have to. So imagine that the x squared term is a placeholder. It's a digit in this number that is like this quote unquote number. So it needs to be there even though it's not actually part of the expression originally. Does that make sense? That's the way I like to think of it, is it's just a digit that needs to be there. So we'll go through the whole process. How many times does x go into 3x cubed? Well, 1 goes into 3 times, and x goes into it x squared times. So we get 3x squared. Then 3x squared times x plus 1 gives me 3x cubed plus 3x squared. And I always like to draw the subtraction in a different color and put parentheses around it to remind myself I'm subtracting that whole expression. I'm not just subtracting the 3x cubed and adding the 3x squared. I'm subtracting the whole thing. So, what do I get? The 3x cubes, they're going to cancel. That's by design. And do I get 3x squared or do I get negative 3x squared? Excuse me. Isaac says negative 3x squared, and he's absolutely correct. Get a negative 3x squared. And then we'll bring down the x and the 5, so plus x plus 5, and we continue the process. How many times does x, the leading term of our dividend, or sorry, our divisor, the leading term of our divisor, how many times does it go into negative 3x squared? Well, 1 goes into negative 3 times, and x goes into x squared x times. Because I need to multiply x by x to get to x squared. All right, and then so we now carry out the multiplication to put the thing underneath it. So negative 3x times x plus 1, that's going to be negative 3x squared minus 3x. And then we subtract that one. And you can use multiple colors or you can stick with red. I'm just going to add some fun and do orange now. The negative 3x squared minus negative 3x squared, that's really negative 3x squared plus 3x squared. Those cancel. And then what do I get? Take a second to do it yourself. If you haven't already done it already. X minus negative 3x. So what do we get? 4x. We don't get negative 2x because we're subtracting negative 3x. So we get 4x plus 5. So we bring that in the plus 5. And then we do it one last time. How many times does x go into 4x? It goes into it precisely 4 times. So plus 4. 4 times x plus 1 is 4x plus 4. And we finally subtracted one last time. The 4x's will cancel. 5 minus 4 is 1. And then we have nothing left. X doesn't go into 1 at all. You can't divide x into 1 without it becoming a fraction. And so At the end of the day, we have that 3x cubed plus x plus 5 divided by x plus 1 is equal to 3x squared minus 3x plus 4 plus a remainder of 1 divided by our divisor, which was x plus 1. How does this thing die so quickly? How does my pen die so quickly? Any questions on that? We'll fill in a little bubble, a little thought bubble or thought cloud in just a moment. Any questions? Nothing? I know it's very exciting stuff, but it's very useful. And we're going to learn another way as well. Long division does take a long time, unfortunately. Yes. Yeah, what's up?
Why yellow and blue? Why is it -3?
Right under the red. Because it's going to be 0 minus 3x squared.
Oh,
So that's why it's going to be negative. All right. Now I'd like you guys to do part A yourselves. I'll set it up for you, and then I'm going to pause the recording so that everyone gets a chance to work through it. And I'll slowly fill in details. So it should be 3x squared minus 2 divided into 27x cubed plus 9x squared minus 24x minus 10. All powers of x are present in the divisor. I didn't need to write a plus 0x in the dividend. Sorry, I always get these two mixed up in my head. There's no missing power of x in the divisor of the dividend. The thing on the inside, the 3x squared minus 2, it is missing an x to the first power term. So you can write it as 3x squared plus 0x minus 2 if you want. It's not wrong to do so. It's unnecessary, but you can do it. So now I'm going to pause the recording. All right, this is what you should get. So you should get 9x plus 3 as your quotient, and your remainder should be negative 6x minus 4. Does anybody have any questions on that? Yes, Dave.
what do you do with the two? Not having to do with like. So the first one is it's 9x.
X.
Right?
Yes.
So do you not include -2?
So when you're trying to figure out what the 9x is, yes. So I was hoping someone would ask that. So you really only need to worry about the leading term. And the way I like to think about it is imagine if you were dividing by 30, you're really not really thinking about how many ones go into it. Like when you've got like 30 divided into something, you're really concerned with the 3 more than you are the 0, right? Like the 0 does play a role, but it's more specifically looking at the 3. That's the bigger thing to do. So that's the idea, is just look at the like the 0, the other stuff does play a role, but not nearly as much as the 30 does. Is that cool? So I'm like in practice, always use the leading term to figure out what this number is going to be. Any other questions? Great question. So what? It only plays a role when you do the multiplication. When you do the 9x times the 3x squared minus 2, that's where I get the minus and 18x. That's where it comes into play. Cool? Any other questions? So it does play a role, just not in the original step, like not in step 1. Okay. So the observation is to notice the degree of the quotient. This will play a role when we talk about synthetic division in a moment. Notice in part A, the degree of the dividend, the thing that's being divided, that's getting divided, it's degree 3, and the divisor, the 3x squared minus 2, is degree 2, and the quotient is degree 1. 3 minus 2 equals 1. In this previous, in the part B, dividend is degree 3, divisor is degree 1, the quotient is degree 2. 3 minus 1 is equal to 2. So that is a key component about them, is that the degree of the quotient is the difference of the dividend and divisor's degrees. That will be important when we talk about synthetic division here in a moment. Okie dokie. So here's a question that you might be wondering. In the last 3 examples, in all 3 of these division examples, I've always rewritten the statement. I've always rewritten the division, right? Here I wrote 14x squared minus 9x plus 2 over 7x minus 1 is equal to this. And I only boxed that portion because that is my answer. But it's important to understand that these things are equal because that allows us to check our work. Because they're equal, what I can do is I can multiply both sides of the divisor and I should get back to the dividend. So case in point, that's the nice thing about the original, the proving version of it. If I know what my quotient and my remainder are, if I take care of it, if I multiply both sides of this equation by d, my divisor, I should get back my polynomial. So case in point, what I'm trying to say is for this last one, if I take x minus 1 or x plus 1 and I multiply my my quotient plus my remainder divided by my divisor, so 3x squared minus 3x plus 4 plus 1 over x plus 1, and I distribute this in, I'm going to get 3x cubed plus 3x squared minus 3x squared minus 3x plus 4x plus 4 plus 1. You're wondering what? Oh, yes, Ava. Oh, the bubble that says the degree of the quotient is the difference of the dividends and the divisor's degrees. All right. So just to explain what happened in this case, I'm distributing it into each one. So when x plus 1 gets distributed into 3x squared, I get a 3x cubed plus a 3x squared. Then when I distribute it into the minus 3x, x times negative 3x is negative 3x squared. Negative 3x times 1, that's in minus 3x. Then I distribute it into the 4. 4 times x is 4x. 4 times 1 is 4. And then when I distribute it into the 1 over x plus 1, the x plus 1s cancel, giving me just a 1. And you'll notice that when you combine like terms, you get 3x cubed. The 3x squareds will cancel. You'll get plus x, and you'll get plus 5. So it is the exact same thing. It's the, like, if you look back up above, that's the dividend. So you can check your work on these things, which is great. That's a really useful trick if these types of questions get asked. Or if you're uncertain, you can always check your work. Any other questions? If not, we will move on to a different division technique other than the long division technique. Because you might be wondering, good God, Phil, do I really have to do that every time? No, not every time. Some of the times. There is a great and quicker way to perform polynomial division. However, there is one big red baboon butt, right? There's a big but statement. This only works, can only happen, can only be used, can only be done if the divisor is of the form x minus c. So we can't use if we're dividing by x squared minus 1, oh, minus 2, or 3x x minus 5 plus 5. Let's write that down and then I'll explain. Synthetic division is awesome. It's a great trick. And it feels a little bit like voodoo at first. And that is understandable. And so I will send out a video once we finish with this area. I'll send a video out on why synthetic division works if you're curious to know what is happening. But if you're comfortable just learning the technique, awesome. That's great. But if you want to know the reasoning behind it, feel free to watch that video. I'll send it out soon. So the divisor, the thing you're using to divide by, the thing on the outside of the bar, right? So in this case, the divisor, God, I know that the pen is low on battery. I keep forgetting to plug it in. Okay. You know what's even better about this is you can't use it when it's being charged. Like, even if I could hold this awkwardly, right? It would not charge the proper way. Even if you use the adapter they give you. Apple and their infinite wisdom. Okay. The divisor needs to be of the form x minus c. So if it was x squared minus c, couldn't work. So I've got an example like x squared minus 2. Can't work because of the x squared. Or if you have 3x plus 5 or 3x minus 5 or whatever it is, the problem is that 3. It needs to be of the form 1x minus a number. So to set it up, you're going to set it up. It's going to look a little different. I think the way Alex does it, they don't do it this way exactly, but you're going to make a bar like that and then a bar like that. And so you're going to set up your synthetic division by putting your C value in the space 1. But make sure you're viewing your divisor as x minus c. So this is x plus 2. So I need to rewrite this as x minus negative 2. So my c value is negative 2. It's not 2. So put your c value in space 1 and put the coefficients of your dividend in space 2. So 1x cubed minus 7x minus 13x plus 15. So a note here is the bar goes right before the constant term. I probably should have added this. If missing power of x add a placeholder. like before. Synthetic division and long division, they still like, the thing is, synthetic division is long division. It's just done in a faster way. That's all, that's really all it is. Synthetic division is just long division done quicker. It's the exact same process, but it looks different. Think of it like we're not gonna get into, don't worry, I'm coming right back to it. But we are going to go over in unit 4, we're going to talk about systems of equations. And the way we're going to solve them is we're going to look at them like 2x plus 5y equals 7 and negative 3x minus 9y or plus 9y equals 8. We will solve them this way. We will solve them by the elimination method and the substitution method. We'll get comfortable with both. But in matrix algebra, in math 251, no, 253. You will learn about how to write these in a matrix. And so you'll write this instead, you'll write it as 2, 5, negative 3, 9, bar, 7, 8, like that. And you can solve it so much faster with matrices. You don't have to rewrite the x's and the y's each time. That's essentially what we're doing. We're trying to avoid writing the variables because the variables are going to be there regardless. So the numbers are the things that are changing that in each problem. All the powers of x are always present in each problem. It's the numbers that are different. So that's what this process is trying to do. So that's step 1. Put your c value. Make sure you're viewing your divisor as x minus c. So we had x plus 2, so we wrote it as negative 2 minus a negative 2. And then in the first space, in space 2, the blue space, put all the coefficients of your dividend and put the bar right before your constant term. Step 2 is drop down the number in the first slot of space 2 into space 4. So let's rewrite everything we had. So negative 2, 1, negative 7, negative 13, 15. We're going to drop down the 1. It's the unique one that happens to it. That always happens with the first one. Then from here on out, we're going to multiply your C value, your space 1 number, by the number that gets dropped down in step 2 and put the result in the next slot in space 3. So let's see that in action. So negative 2, 1, negative 7, negative 13, positive 15. We brought down the 1. And this is the new step. I'll do it in blue. And feel free to ask any questions about the process along the way. What you're going to do is you're going to take this negative 2 and this 1, and you're going to multiply them together and get negative 2 here. And you're going to put it in the next column. Columns aren't really there, but like the next column. And this is taking a lot longer right now. You're like, how could this be faster than synthetic division? It's because we're showing all the steps. I'll show you how fast it can be in just a moment. So then we go into step 4. We're going to add down and then place the result in step 4. So you got negative 2, 1, negative 7, negative 13, 15. We brought down the 1. We multiplied negative 2 by 1. We got negative 2. And now what we're going to do, which I'm going to do in purple. No, not purple. Orange. Does orange show up okay? Yeah. We're going to take these two numbers and we're going to add them together to get negative 9. I know that negative 9 is hard to see, but let me zoom in then so you can see it a little bit better. So we take the -7 and the -2 and we add them together to get -9. Then the last step is the iterative process. Now we're going to repeat this idea of multiplying diagonally and adding vertically until all the columns have been filled out. So we got -2, 1, -7, -13, 15. The first column is always the unique one, but everything else after that is multiply diagonally, add vertically. So what I mean by multiply diagonally, take the C value with the thing on the bottom. We're multiplying diagonally. -2 times 1 is -2. Then we add vertically. Multiply diagonally, then add vertically. So -2 plus -7 is -9. Then we continue the process, multiply diagonally. -2 times -9 is +18. Then add vertically. -13 plus 18, that's +5. Multiply diagonally. -2 times 5 is -10. And then we will add vertically. 15 plus -10 is +5, and we are done. How are we done, Phil? That's not a polynomial. That's not a remainder. That's not a divisor or a dividend or a quotient. It is. It's the coefficients. The first three numbers, the numbers before the bar, the vertical bar, these are the coefficients of the quotient. And this is the remainder. Any questions on that? So we took a degree 3 polynomial and divided it by a degree 1 polynomial. The dividend was degree 3. The divisor, sorry, it's coming back up. The divisor was x plus 2. It's degree 1. So what should our quotient be? What should our quotient be? 2. 3 minus 1 is 2. So, and that's always going to be the case with synthetic division. It's always going to be 1 dropped down by 1 degree because you're always going to be dividing by x minus c, a degree 1 polynomial. So your quotient will always be 1 degree less than your dividend. Our dividend was degree 3. Our quotient is degree 2. If our dividend was degree 8, our divisor was degree 1, it will be degree 6, so on and so forth. So we have that x cubed minus 7x squared minus 13x plus 15 divided by x plus 2 is equal to 1x squared minus 9x plus 5 plus a remainder of 5 divided by a divisor of x plus 2. I wrote the 1 in front of the 1x, in front of the x squared to show where it's coming from. But normally you just write x squared. That is the process. It's all about bringing the first number down, in the first column down, then multiplying diagonally, adding vertically until you finish it off. It's a very, very iterative process, and I want to show you how fast it can be. Does anybody have any questions? So this one right here, x cubed minus 4x squared plus 9x minus 10 divided by x minus 1. This is how fast it can be done. Done. X squared minus 3x plus 6 plus negative 4 divided by x minus 1. How quick was that? Very quick. That was less than 30 seconds. Instead of having to do it with long division, could you like try and do this when you're bored this weekend? Doing it with long division is going to take a lot longer. It's going to take probably 2 minutes. I did that in less than 15 seconds. So it's very, very quick. It's awesome, but it is niche. It only works with x minus c. So then you might be wondering then, well, and so we'll rewrite this. We'll write this better. We'll do this one together after the break. But you might be wondering, why even bother learning this method? Yes, it's faster, but there's so many different types of situations where you can divide by polynomials that aren't of the form x minus c. So why bother learning this method at all? And the answer to that question is that whenever, like, there's a thing we're going to go over in just a moment called the remainder theorem and therefore the factor theorem. And that's going to show us why it's useful. So suspend disbelief for just a moment, and I will show you why we care about synthetic division in just a little bit. Let's take our first break. Let's come back at 12:05. Okay, people watching the recording, do some push-ups. We're back, and we're going to practice our synthetic division. I'm going to change this one here. I'm going to change this to 3x to the 4th. Let's do 5x to the 4th. Just to throw it off a little bit, just to change it up, because I actually taught this in my other class, and they were wondering why all the leading coefficients were 1. The dividend can have any numbers it wants. The dividend, it doesn't matter what the coefficients are. It's just with the divisor. It needs to be 1x minus something. So with this top one, it's x minus 1. So our c value is 1. It's already in the right format. So we set it up by putting 1 there, and then we put all the coefficients in this little slot. So 1x cubed minus 4x squared plus 9x minus 10. All the powers of x are present. We get that set up. Then we bring down the first column. So we bring down that 1 from the first column. And then we go through and multiply diagonally and add vertically. So 1 times 1 is 1. Adding vertically, negative 4 plus 1 is negative 3. 1 times negative 3 is negative 3. 9 plus negative 3 is positive 6. 1 times 6 is 6. Add vertically, negative 10 plus 6 is negative 4. So we get our final answer. We had a degree 3 dividend. So we're going to get a degree 2 quotient. So it'll be 1x squared minus 3x plus 6 plus negative 4 divided by x minus 1. Write your result as quotient plus the remainder divided by divisor. Now with part B, be careful. There's a missing power of x. There's no x to the first power term. We need a placeholder. So when we set this up, notice that c, what's the c value here? Is the c value 3 or negative 3? You have to divide by an x minus c. It's already in x minus c format. So the c value is 3. If it was x plus 3, we need to write it as x minus negative 3, and that would be the situation. But it's x minus 3. So our c value is 3. And then we set up our little division. So 5x to the 4th minus 2x cubed plus 3x squared plus 0x minus 4. Any questions on that? Yes,
I think we changed A's x minus 1. You did.
We did. It was originally a -1 here, and so it's already in the right format. So it's that's why we just wrote a 1. If it had been +1, we would have wrote a -1. That x minus h situation is going to show up so many times in this course, by the way. So I'd like you guys to go ahead and perform the synthetic division. Bring the first column down, then multiply diagonally, add vertically. You might need to use a calculator. Am I right? Did I get that right? No, I did not get that right. Dope. Promise I can do algebra. Whew. All right. So you should get 5x cubed plus 13x squared plus 42x plus 126 plus 374 divided by x minus 3. Right? Let's bring another 5. 3 times 5 is 15. -2 plus 15 is 13. 3 times 13 is 39. 39 plus 3 is 42. 3 times 42 is 126. 0 plus 126 is, of course, 126. 3 times 126 is 378. Plus the -4 gives me 374. And if you're really bored, multiply that entire expression by x minus 3 and see to make sure that you get back the original dividend, the 5x to the fourth minus 2x cubed minus plus 3x squared minus 4. And it should all work out. Okay. The next one, 2x to the fifth minus 6x cubed minus 14x divided by x squared minus 2. Wait a minute. We can't use synthetic. I pulled a fast one on you. Can't use synthetic. Sad days. We have to do long division. If it had been x minus 2, we could use synthetic, but we can't because it's x squared. So x squared divided in minus 2 divided into 2x to the fifth. Notice that there's no x to the fourth term, so I have to add a placeholder. Then minus 6x cubed. Oh, there's no x squared term. So plus 0x squared. Then minus 14x. And there's no constant term either, so plus 0. Go ahead and perform this long division. Unless there's any questions on this setup. I'm going to pause the recording so that, and then we'll come back together. Okay, so to go through it, how many times does x squared go into 2x to the fifth? It goes into it 2x cubed times. Multiply 2x cubed into x squared minus 2. You get 2x to the fifth minus 4x cubed. Luckily, there was no x to the fourth term that came out of that. So when we subtract it, the x to the fourth just goes away. And then negative 6x cubed minus negative 4x cubed, that's really plus 4x cubed, so it gives you a negative 2x cubed at the end of the day. Bring down the plus 0x squared minus 14x plus 0. And then how many times does x squared go into negative 2x cubed? Well, it goes into it negative 2x times. Take care of it, and you end up with a negative 18x at the very bottom. And x squared does not go into negative 18x. It's too high of a power. So we're done, and that's our remainder. And that is all she wrote there. Any questions on that? Okay. So let's talk about why we use synthetic division. First and foremost, a preliminary result. This isn't super useful for us at all anymore in mathematics. It was a while back before we had calculators. So I'm not going to spend too much time on it, but the remainder theorem says that if f is a polynomial and it's divided by x minus c, then the remainder will be f of c. So it's saying if f of x is equal to 2x cubed minus 4x squared plus 5x minus 3, find f of negative 2. Now, we could do it the old-fashioned way, brute force. F of negative 2 would be equal to 2 times negative 2 cubed minus 4 times negative 2 squared plus 5 times negative 2 minus 3. And that would end up being negative 45. So that is the way we should do it in this day and age, because we have calculators. But imagine if you didn't have a calculator. This method would be very, very quick, as you'll see in a second. Remainder theorem. Option. So if you want to divide, like the remainder is f of c. If you divide by x minus c, the remainder will be f of c. So if we want to find f of negative 2, we'll just divide f by x minus negative 2. And x minus negative 2 means our c value is negative 2. We'll divide that in. So 2x cubed minus 4x squared plus 5x minus 3. Put a bar right before your constant term. And before the synthetic division, we're going to need to be able to use it. So I want you to complete this synthetic division to show you why mathematicians back in the day, before calculators were a thing, why they really liked this. Your bottom row should be 2, negative 8, 21, and negative 45. You get the same number. Ta-da! Pretty exciting. Not really. But you got to think about it from the perspective of a mathematician back in the day. If this was a big number like 5, imagine trying to compute 2 times 5 cubed, or let's do 7. Do you really want to calculate in your head 2 times 7 cubed minus 4 times 7 squared plus 5 times 7 minus 3? That's a pretty annoying number to calculate in your head. We have calculators, so this theorem is kind of a moot point. However, it is used, the main reason why I'm even mentioning it is this theorem proves the factor theorem. And what the factor theorem says is that if f is a polynomial, then f of c equals 0 if and only if x minus c is a factor of f. That's a very useful fact, as we'll see in a little bit. So, the forward direction of this if and only if statement, that's just a true statement. That's the definition of what a zero is. If f of c equals 0, then x minus c is a 0. And then on the flip side, if it was a factor, then you'd get a remainder of 0. So f of c would equal 0 by the remainder theorem. That's the reason why that theorem is even mentioned. It's for the factor theorem. That's an if and only if statement. So if you know that x minus c is a factor, then you automatically know that f of c is equal to 0. The far more useful direction is the forward direction. If you know that f of c is equal to 0, then you know x minus c is a factor. So let's see that in action. Is x plus 5 a factor of f of x equals 2x to the fourth plus 12x cubed minus plus 6x cubed minus 5x plus 75, excuse me. So we're trying to determine whether or not it is. If x plus 5 was a factor, then by the way, this is x minus -5 to get it in the format of x minus c. So if that were a factor, then f of -5 would equal 0. So we could use the and so this is the other reason why we might want to use the remainder theorem to figure this out. If it does equal 0, when we plug it in, we do it by brute force. Then it is a factor. But if we want to factor this fully, just getting 0 for our answer doesn't tell us the factorization. But if we do the synthetic division, we will find out the factorization. So case in point, let me show you. So let's use the remainder theorem. Remainder THM to figure out. So -5 is our C value divided into 2x to the fourth plus 12x cubed plus 6x squared minus 5x plus 75. Put a vertical bar right before our constant term and carry out this long division, the synthetic division. Want to pause it so we can do that? So you should get this, and so when we divide it by x minus 5, or x plus 5, with synthetic division in this case, we get a remainder of 0. And the remainder, so by the remainder theorem, f of -5 does equal 0. Because the remainder is f of c. The remainder you get when you divide by x minus c is f of c. So because it does equal 0, by the factor theorem, x plus 5 is a factor. Let's write that down. And so you might be like, as I said, though, we could have just plugged in f of -5 to see if it worked. And I guarantee you, if you do that, so 5 to the fourth power, 525, 125, 625. 2 times that is 1,300. Regardless, use your calculator. You'll get that it's 0. But this gives us far more information. In fact, in fact, f of x equals x plus 5 times 2x to the third plus 2x squared minus 4x plus 15. Let's use green. So the reason why the remainder theorem is a little bit nice is that if you do end up getting 0 when you divide it by it, then that means you've already found what the factorization of the next piece is. If you know that x plus 5 is a factor, then when you do the long division, this gives you what the next piece will be. So that is nifty. You could have, like, if it was just, if like, as this problem states, is x plus 5 a factor? Then you can just plug in -5 into the function and see if it works. If it does, awesome. If it doesn't, then the answer is no. But if it was to ask you, is x plus 5 a factor? And if so, factor the polynomial, then using the remainder theorem would have been far more useful because it would have immediately told us what the factorization is. So it was trying to do it faster than if we had done it the other way by brute force, then we say, okay, it is a factor. Now I need to do the long division anyways. So it adds on, like, it cuts out a middleman. It cuts out a little step. Is that okay? Any questions on that? All right. Now, there's a million different factor theorems. And the one that the textbook has, I don't think is good enough. So I decided to make my own one, and I called it the big boy factor theorem to make sure I was getting relating to all you Gen Zers out there, right? Do you guys still use boy on occasion? Let that kid going, yeah, boy. Anyways. So this is the factor theorem. All of these statements are true. If one of them is true, then all of them are true. Let f be a polynomial and c be some real number. Then, if f of c equals 0, that's one option. F of c equals 0. That would mean that x minus c is a factor of f. The other option is that f of x equals x minus c times blah, where this is the quotient when dividing by x minus c. So f of c equals 0 is one option. X minus c is a factor of f. That's the second option. F of x equals x minus c times something, but no remainder. That's another option. Then x equals c is a root / 0. And then last but not least, f of x divided by x minus c has remainder 0. Whew, that's a lot of things to write. The first three are the most useful parts of it. The fact that x equals c is a root, that's just by definition. If f of c equals 0, then it's a root. That's just a fact. That we learned that in 2.2 at the very, very beginning, on page 2, if I remember correctly. That if f of c equals 0, then x equals c is a root. That's just a fact. But the far more useful facts are these first three. So if you have any of these three facts, if you have any one of them, you have the other three, other five or other four. I can count, I promise. But the first three are the most useful. The last one is not nearly as useful as any of the other ones, but it's still a fact. So Is x equals 1 a factor of f? What about x equals negative x plus 2? So, and if it is, factor it, is probably what I should say. So if it's just asking whether or not they're factors, which this one is, then you could just plug in f of 1. If f of 1 equals 0, then it is a factor by the big boy factor theorem, right? If f of 1 equals 0, then x minus 1 is a factor. That's like the first two bullet points. What about x plus 2? If x plus 2 equal, if we're asking whether or not that's a factor, that's x minus negative 2. So if we find f of negative 2 to be 0, then yes, it would be a factor. But what I probably should ask in this problem, if so, factor it. So we're going to use the remainder theorem. So x minus 1, you're going to set up the synthetic division, 1. All the powers of x are present. Always be on the lookout for that. So 2x cubed minus 1x squared plus 2x minus 3. All powers of x are present and accounted for. Bring down the 2. Multiply diagonally, add vertically. 1 times 2 is 2. Add vertically, you get 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. Negative 3 plus 3 is 0. So, yes. This means that f, let's use blue. Let's use green. F of 1 equals 0. Check mark. So the answer is yes. And therefore, f of x could be rewritten as x minus 1 times x 2x squared plus x minus plus 3. So when we did the long division, we got a remainder of 0. That means that x plus 1 is a factor. You can use the big boy factor theorem. I'm sorry. Big boy factor theorem in a myriad of ways. We got a remainder of 0. That's the final bullet point. That automatically means the second bullet point, x minus c is a factor. So you can use this in a bunch of ways. It's a really, really useful theorem. Probably the most one. Oh, I originally wrote this as the thick with 2 C's. Because that's what Mackenzie says. But then I realized that was probably a little bit someone told me that was inappropriate, and I guess that probably makes sense. Anyways, we're just gonna be like Dory and forget I said that. Okay. X equals 2, x plus 2. This time we're gonna do negative 2. And so 2x cubed minus 1x squared plus 2x minus 3. Bring down the 2. 2 times negative 2 is negative 4. Negative 1 plus negative 4 is negative 5. Negative 2 times negative 5 is positive 10. 2 plus 10 is 12. Negative 2 times 12 is negative 24. We get negative 27. So that is equal to, that's not equal to 0. So nope. And we're done there. Not equal to 0, so x plus 2 is not a factor. Any questions on that? So you can do you can do synthetic division to check. So hopefully now you see with this, I meant to mention it and I never really, I said I was going to mention it, but I forgot to. This is why synthetic division is useful. Because of the factor theorem, the big boy factor theorem. X minus c is a factor if and only if when you divide it by, you get a remainder of 0. You're always dividing by 1x minus a c value. So synthetic division is super useful when it comes to polynomials and finding their roots. That's the reason why we study synthetic. For any reason, like Anything else besides that, we'll use long division. But when it comes to this one, synthetic is great. Factor m of x equals 3x to the fourth minus 11x cubed minus x squared plus 9x plus 19x plus 6. Given that m of -1 and m of 3 are equal to 0. Okay, so this one I deliberately wanted to mention because looking at this one, if I did not give you this, if I omitted this fact, in order to find out how to factor it, it would take a long, long time. Because at this moment, we don't have any way to factor cortex. There is no real method. In fact, that's a true statement. There is no guaranteed method to find the zeros of a quartic. There's a cubic formula, there's a quadratic formula, there is no quartic formula, there's no quintic formula, there's no hexic formula or anything like that. After 3, there's no guaranteed formula. So that was a really, really important theorem that got proved in mathematics by a 19-year-old, by the way, to make you feel inadequate for a second. Like when we were learning about it, then like when I was in grad school learning about it, it's like, by the way, this was invented by a 19-year-old, and I'm sitting here at 26, and I'm still struggling with that concept. And he was able to prove it at 19. Emmanuel Galois proved that there is no quartic formula. There is no, for any degree above 4, there is no formula to find all the zeros, which is pretty fascinating. Why it stops at 4, that's a good question. But that requires a lot more mathematical knowledge that we don't have. But either way, point being is that right now we have no way of factoring this. So once we have this information, so that's what we're going to write here. Since, wrong font. Since m of -1 equals m of 3 equals 0, x minus -1, that's x plus 1, and x minus 3 are factors of m. Because we know that m of -1 equals 0, we know that x minus -1 or x plus 1 is a factor. And because m of 3 equals 0, we know that x minus 3 is a factor by the factor theorem, right? Going back up, don't worry, I'm coming right back down to it. But if, like, instead of f, we're calling it m, but m of -1 equals 0, that means that f of x will be equal to x minus 1 times the quotient you get by dividing by x plus 1. So we can start with whichever one we want. Let's just start with x plus 1, which x minus -1. So we'll put a -1 here and do the synthetic division. 3x to the fourth minus 11x cubed minus 1x squared plus 19x plus 6. All right, bring down the first column. Go ahead and do the synthetic division. I'm going to pause it so that people watching the recording, you should do it yourself. Pause the video and do it yourself. Division done. So this is what you should get. You should get in your bottom row, you should get 3, -14, 13, 6, 0. Since you got a remainder of 0, that means that it is a factor, which we should already know, right? M of -1 does equal 0. And so by the big boy factor theorem, I'm going to say it every single time like that, I don't care, is going to be x minus -1 or x plus 1 times 3x cubed minus 14x squared plus 13x plus 6. Now, here's where students go wrong on this problem. So we have just broken down the polynomial. We've broken down m into one part that's a binomial, like the x plus 1, and then a degree 3 polynomial. We've done that. Cool. However, what a lot of students will mistakenly do now is they'll also do this. They'll do this and then write, come on, let me grab it. Okay, then m of x is going to equal x minus 3 times 3x cubed minus 2x squared minus 7x minus 2. And they're not going to get anywhere. Because what you've done here in the black versus the red, you've just found two different ways to write m as a product of a binomial and a cubic. If you FOIL these out, you'll get back to m. So how do I go from here? How do I get it to break down further? Because if I can break it down again, if I can break it down and get one more factor, then I will be able to have quadratic, and I can factor quadratics. I know how to do that. We've learned how to factor quadratics, ax squared plus bx plus c, using any of the methods that we know and love. So the trick is that this is up above, this is an unfactored way to write m. 3x to the fourth minus 11x cubed minus x squared plus 19x plus 6. And what we just found was a factored version of it, not a completely factored version, but a factored version. And since m of negative 1 equals 0, you'll notice that if you plug in negative 1 into here, you'll get something here that there'll be some number times 0, and it equals 0. But the same is true with 3. But if I plug in 3 here, it'll be 4. And what do we know about the zero product rule? If it equals 0, then one of the factors must equal 0, right? We know, so I'm going to show you real quick. Don't write this down. We know that m of 3 equals 0. So you got 3 plus 1. 3 plus 1. And whatever this is, it has to equal 0. Whatever this is when we plug in 3, that has to be 0. Otherwise, we get a number times another non-zero number that would never equal 0, because 0 can only happen if one of the factors is 0. So the point being is that since x minus 3 is a factor of m, capital M, it must be a factor of this as well, by necessity. There's no other way around it. We know that x minus 3 has to be a factor of m, and since x minus 3 is not a factor of x plus 1, the only other logical conclusion is it must be a factor of 3x cubed minus 14x plus 13x plus 6. Let me say that one more time because we were writing at the same time. From the fact that m of 3 equals 0 by the big boy factor theorem, that means that x minus 3 is a factor of m. We've written m as a new factorization. It's not completely factored. That would be breaking it down into all little x minus a's or x minus c's or whatever. And since x minus 3 is not a factor of x plus 1, it must be a factor of 3x cubed minus 14x squared plus 13x plus 6. So instead of dividing m, the original version, by 3 with synthetic division, we're going to divide that one that's highlighted in blue. So we'll take 3 and divide it into 3x cubed minus 14x squared plus 13x plus 6. All powers of x are present and accounted for, so we don't need to add any placeholders. And go ahead and take care of this synthetic division and then factor it. Because once you've done this, you'll be able to factor it completely. Well, actually, no, we'll do this one. Like, I realize there's a little more nuance that I need us to do. So bring down the 3. 3 times 3 is 9. 9 plus negative 14 is negative 5. 3 times negative 5 is negative 15. Negative 13 plus negative 15 is negative 2. 3 times negative 2 is negative 6. 0. So, lo and behold, as I said, it was a factor of the cubic polynomial. And so what that work has just showed us is that what this tells us is that 3x cubed minus 14x squared plus 13x plus 6 is equal to x minus 3 times 3x squared minus 5x minus 2. Any questions on that? So once again, because we did synthetic division on that cubic that's underlined in blue, we now know that that cubic is broken down into an x minus 3 and a 3x squared minus 5x minus 2. So we can rewrite it above. We can rewrite m now. Rewrite m. M of x is therefore x plus 1. We had that from the beginning. And then we just took the blue cubic and we broke it down. We were here. Now we can break that cubic down into this. So now it is x plus 1 times x minus 3 times 3x squared minus 5x minus 2. And this is a quadratic, and we know how to factor quadratics. So we're going to factor this like normal. And we get that m of x is equal to x plus 1 times x minus 3 times, okay, if we're doing the guess and check, which is the way I like to do it, minus 2 and or plus 1 and minus 2, right? Yep. Now, of course, if you're doing this on your own, by the way, there's feel free to use your scratch paper, right? Use some scratch paper to factor it. I don't need to see that anymore. I test you on that in exam 0. Now I assume that you guys can factor on your own. So you can do that factorization stuff on scratch paper. You don't need to show that work anymore. Okay? Any questions? All right. Now we come to a very fun problem, ones that are near and dear to my heart. Create the equation of a polynomial. I love creating polynomials. That passes through the point -2, 100, whose zeros and their multiplicities are listed below. Okay. So we know what the zeros are and we know what their multiplicities are. So by the big boy factor theorem, by big boy theorem, f of x equals, leave a little bit of space because I'm going to mention something, by the way. So leave a little bit of space and then write, okay, one of the zeros is -4. So that means that x minus -4, so x plus 4, is a factor. But in particular, it is only multiplicity 1. So it has to have a power, an exponent of 1. Then we know that -1 is a 0. So that means that x minus -1, or plus 1, that is also a factor. But it has a multiplicity of 3. So I have x plus 1 cubed. Then we know that 0 is a root. So x minus 0 is a factor. But it's also raised to the first power because the multiplicity on 0 was 1. And last but not least, since 2 is a 0 of the polynomial, x minus 2 should be a factor, but it's going to be squared because it has multiplicity 2. So that's what we get. And I put a space for a reason. This polynomial that we've written here, this polynomial has those zeros. In fact, f of x equals, let's use blue, a. Any for any a value, this function will have the designated zeros designated roots, let's say called roots, with corresponding multiplicities. Sorry, I'm going to shut down the program for a second because it's wigging out. It's going to reload in just a moment. Sorry for the delay. Wow, it went really far back. Okay, cool. For any a value, this function that I've written will have the designated roots to the corresponding multiplicities. Because remember, at the end of the day, an a value, all it does, so if a is positive, it'll be a vertical stretch or compression. If a is negative, it'll be a reflection across the x-axis, and it might be a vertical stretch or compression, but that's not going to change the zeros. As we saw when we were in 1.6, whenever you were on the x-axis and you vertically stretched or you reflected, they always stayed on the x-axis because that's where they are. So, you can choose whatever a value you want if you're given just the zeros and the multiplicities. So if it just said create a polynomial that has those zeros and those multiplicities, you could just write a 1 and call it good. Like, don't even bother writing it. However, there is only one that passes through -2, 100. There is only one of those polynomials. I could pull it up. It would be hard for me to set it up. Maybe if we have time at the end, I could show you on Desmos. But if you were to graph a polynomial x plus 4 times x plus 1 cubed times x minus 0 times x minus 2 squared, and you just kept plugging in random a values, or you used a slider to choose the different a values, you'd see that they'd get bigger or smaller, or they'd flip and stuff, but there would only be one choice of a that would actually hit that point, -2, 100. So we need to find so let's find the a. And how would I do that? How would I do that indeed? Well, if -2 is on the graph of this polynomial, what do I know about f of -2? -2, 100 is on the graph. That implies that f of -2 equals 100. So remember, that's the big connection. If a comma b is on the graph, then f of a is equal to b, because you have your x coordinate, and that gives you a y coordinate. In function notation, that's inputting an x value and getting a y value. You take in an x value, -2, and you spit out a function value, a y value, 100. So we can now replace all the x's in f with -2's, replace the f of x with 100, and solve for a. That a will be the only variable left over. So we have f of -2 is equal to a times -2 plus 4 times -2 plus 1 cubed times -2 minus 0 times -2 minus 2 squared, and that has to equal 100. And that's going to be -2 times -1 cubed, so -1, so that's +2 times -2 is -8 times -4 squared, that's 16. That should be 64. Let me just triple check. -2 times -1, so just 2 times -2 times 16, 64. So it's going to be 64a equals 100, which gives me that a is equal to 100 over 64, which reduces down to 25/16. Or wait. Yeah. 25/16. So f of x at the end of the day is 25/16 times x plus 4 times x plus 1 cubed times x minus 0 times x minus 2 squared. Any questions? So if they don't give us a point that we can work with, there's no way to find out what a specific a value is. So you can just leave a to be 1. If it doesn't designate a point on the graph that you can utilize, there's no way to solve for an a value. So we're just looking for a generic any polynomial that will solve for it. But if they give you a specific point, if I give you a specific point, you can find an exact polynomial that works. And so last problem, and then we might go over and we'll go over the challenge problem because it's fun. It's this one. We're going to add a little bit of spice to the previous problem. Just a little bit of let's add a little bit of, I don't know, just white pepper. White pepper seems to be more spicy than black pepper in my experience. So the graph of a polynomial g is given below. Find a possible equation for g. And a possible one. So, okay. It didn't give me the zeros. It didn't give me the multiplicities. Yes, it did. It just gave it to you in a different format. So what are the zeros of this polynomial? What are the roots? As a reminder, a zero or a root is where it crosses the x-axis. It's an x-intercept. So we have a 0 at -1, a 0 at 2, and a 0 at 4. Okay. So don't write this down. Like I'm going to write this over here. F of x, we know then it would be a. So we don't know what this a value is because there's a million polynomials that have those zeros. But it's going to be x minus -1, so x plus 1 times x minus 2 times x minus 4. And that's what John Doe's student writes, but he's wrong. And you know what? Let's go with Jane Doe. We haven't done Jane, like it's always been John. John's had enough being made fun of. Let's make fun of Jane Doe this time. So Jane Doe writes this, and she's got it wrong. Why? We're not taking into account multiplicity. And we know how to find multiplicity. Even though we haven't really done it before. So notice that it says find a possible equation. Because there's no way to know exactly the multiplicity, but we do know at least that the multiplicity is even. Right? This is an even multiplicity 0. Because it bounces. Because it bounces off and stays on the negative side of the x-axis, It has to be an even multiplicity. Now, whether it's degree 2, multiplicity 2, multiplicity 4, multiplicity 5 billion, that's up for interpretation. It's probably not going to be 5 billion. That would be obscene. And this graph would be way too crazy. But let's assume 2. Because it doesn't look too jagged, right? It doesn't look too jagged. It's not really wiggly at all. It just kind of looks like 2. You could use 4 and I would still give you full credit. If I gave you this graph and you assumed that the multiplicity was 4, 100% still. But one possible answer would be a multiplicity of 2. Now, is the root at 2 even or odd? The root at 2. Odd, because it crosses through. And the same thing is true with 4. Now, if this was on an exam, remember, I don't care too much about your understanding of the jaggedness. So if you made them both multiplicity 1, that would be 100% for me. However, since this is our notes, let's be accurate. The multiplicity of these, the 0 at 2 should be a higher multiplicity because it has more jaggedness. It has more wiggle than x equals 4. They're both odd. Let's assume that 4, we've seen it before, that basically whenever it's a straight line through, it's a multiplicity of 1. So this one, odd multiplicity with no jaggedness. Let's assume 1. And then this one's also odd multiplicity with jaggedness, with some jaggedness, I guess we should say, with some jaggedness. Let's assume 3. But you could use 5. You could use 7. You could use 201. If this is a question on the exam and you write that it's going to be x minus 2 to the 201, I'll give you full credit. I'll give you full credit for that. It'll give me a little bit of a lull, as the kids say. So with this information, we now know, with all of this information, we know that f of x will equal a, which I'm going to do in pink, because we don't know what that a value is, times x minus -1, so x plus 1 to the 2nd power, though you could choose the 4th power or the 6th or the 8th, times x minus 2 to the 3rd power, though you could use the 7th or the 5th or whatever, and then x minus 4 to the 1st power. Though you could technically get away with saying the 3rd power if you really want to, but whenever it's a kind of a straight line through with no wiggle, it's gonna be multiplicity 1. So the only one that really is up for interpretation, the 0 at -1 and the 0 at 2, those ones are up for interpretation. Those are the ones that definitely could be different multiplicities other than 2 and 3. You can do 4 and 5 or 6 and 7, whatever it may be. Okay. Now the question is, can I find a specific a value? Yes, there is a given point. Now, if this was on the exam, I would be making sure to put a solid dot here. I'm gonna do this one in pink. There's an initial condition, f of 0 equals -4. Allows us to solve for a. If they didn't give us what the y-intercept was, we wouldn't be able to solve for a. If they didn't give us an additional point. So maybe on the exam, it might be that I give you the y-intercept. It might be that I give you like a point right here and say that f of 3 is equal to 2. But either way, no matter what happens, we can solve for that. So f of 0 equals a times 0 plus 1 squared times 0 minus 2 cubed times 0 minus 4 to the first power. And that has to equal -4. All right, and that's going to be 1 squared, which is 1, -2 cubed, that's -8, times -4, that's positive 32. So 32a equals -4. Divide both sides by 32, and you get that a is equal to -1/8. So f of x equals -1/8 times x plus 1 squared times x minus 2 cubed times x minus 4. And that is one possible polynomial. If you change the multiplicities to 4 and 5, or 4 and 7, or 2 and 5 and 2 and 7, you will get a different a value because your multiplicity is going to be different, which is going to make your graph look a little different. But the process is still the same. You're still going to plug in 0 and set it equal to -4 and get a different value. What's strange is that if you make it, if you only change the negative, the multiplicity on 2, or on -1, 0, it actually won't change the value, which is pretty strange. It has to do with the fact that it's 1 squared. But either way, any questions on that? Wasn't that cool? You could just be given a polynomial and you can figure out what the equation would be just by knowing its zeros. And by the way, our leading coefficient will be negative, which lines up with the fact that this thing should fall on the left and fall on the right. Count out the multiplicities. 2 plus 3 plus 1, that's 6. This is an even polynomial. It's a degree 6 polynomial. So it either goes both up or both down. But since our a value is negative, it does fall in line with what the shape ends up being. Okay, last one. The challenge problem. Suppose that f of x is equal to kx squared minus 16x plus k squared, where k is some fixed constant, some number. Find the values of k for which x minus 2 is a factor of f. All right, I'm going to add in a little extra page. So write this on the back of the page or something. So how do I do this one? This one we've never seen before, but that's not a reason to be scared. Just because you've never done something, we don't need to be scared of it. Let's be brave. What would it mean, based on the big boy theorem, feel free to look back on it, if x minus 2 is a factor? What would it mean if x minus 2 is a factor? What we're trying to do is we're trying to make sure that x minus 2 is a factor. And if x minus 2 is a factor, what can you tell me about f? That's right. Joy is absolutely correct. If x minus 2 was a factor, then f of 2 would equal 0. Okay. That means I can plug in 2 for x and set the whole thing equal to 0, and that will hopefully get me there. Let's see what happens. F of 2, the mistake that a lot of students will make is they'll try and plug in 2 for k. But remember, f is a function of x. It says f of x here. So if I'm plugging in 2, I'm plugging in 2 for the x's only. So this would be k times 2 squared minus 16 times 2 plus k squared. And that has to equal 0. F of 2 equals 0. And that, let's simplify it. Let's take care of some simplification here. We got k squared. Oh, well, let's write it fully before we go crazy. 4k minus 32 plus k squared equals 0. Now let's write that rewrite that in the proper order. So k squared plus 4k minus 32 is equal to 0. That's a quadratic. We can factor and solve that, or since we don't really need to use the factorization, we can also use the quadratic formula. Either way would work. But this one does factor nicely. It factors to k plus 8 times k minus 4. So k equals -8 or +4. Boom. Done. Any questions on that? Wasn't that a cool one too? That was clever. It's a fun problem. No, probably not. I want to get out of here. I get it. I get it. Okay. I have your exams. I'm going to pass them back to you guys as per usual, as like last time. If there's any mistakes or if you think you were graded unfairly, please let me know and I'm happy to look into it and either give you points back or explain why I graded the way I did. I am human. I make mistakes, so it's okay to ask me for those things. I will not take offense to it. I know that I'm not perfect. And then otherwise, you have a week from today. So next Wednesday, you need to turn in your exam redo for points back. As we saw with these ones, I put the redo problems on the back of them so you know exactly where to put them and everything like that. And then what's it called? Anything else that I wanted to mention? Just as a reminder, it needs to be done by you and your brain alone, and any resources that have a non-solving component, but you can always, of course, ask me for help. You can always email me or come to my office hours and ask questions about it. I'm happy to do those things. Otherwise, you guys have a great rest of your day, a great weekend. Avoid the social media. It's not good for you. Avoid the endless scroll. It's even worse for you. And I'll see you guys on Monday. People watching the recording, I'll send them out. Like if you weren't here, I'll send them out via email.